We have a large glass paperweight that has been in the family for a long time. We don't want to get rid of it, but it just sat there. If it was lit up, it would be more exciting, so an Illuminator project was born. There have been several iterations, but the current one consists of an Arduino Nano and a disc with 7 RGB LEDs on a small circuit board. The wiring involves just 3 wires, 5 volts, ground, and a data line. With just one line, you control the color and brightness of each RGB LED. Here's how the code works. The Arduino code, you have an include statement that includes the Pololu LED strip library. You define which pin on the Arduino the LED strip data line will be, in this case 12. You define the number of LEDs, in this case 7. It sets up an array to handle the colors of each LED up to the number of LEDs, LED count, and we define a variable S for the number of seconds to hold each color. We'll start with maroon. We can use numbers 0 to 255 for each color. We'll use 64 red and 32 blue to make maroon. It then populates all of the LEDs with that color, so I equals 0 to LED count. The color of I is the color, and then when it hits LED strip dot right, that's actually putting those colors into the LEDs, and then the delay S times 1000 delays us for 3 seconds. The second color to come up is cyan, which is 50-50 green and blue. We didn't want it extremely bright, so we used 51 and 51. The rest of the code is the same as maroon. For red, all of the color will be red. 64 is the right brightness for our project. No green, no blue. For green, no red, no blue, just green. Again, 64 for the amount of green we needed. Blue, 64 works as well. For yellow, it's 50-50 red and green, and 32 was bright enough for our yellow to work. To hold the Nano LED disc and paperweight, a 3-piece case was designed consisting of a base, a Nano holder, and a lid to hold both the paperweight and the LED disc. For the base, we have a difference and a union to make up this base. The union is made up of 2 cubes, one translated down 4 units to make the base of it. Then after the union will be the things that are subtracted out. We subtract out a cube that hollows out those initial cubes. If we take that one back out and re-render, you can see that it's got a solid block there instead of being hollowed out. We'll put that back in, re-render. Then there are Arduino mounting holes. We don't actually use those for this project because we're making an insert for holding the Nano, but you can mount it in there permanently if you want with some bolts. There are recess holes to allow the heads of the bolts to be recessed in as well. Last thing then is a hole for the micro USB cable to attach to the Nano while it's installed. For the lid, we have a difference and a union again. We have 2 cubes in the union portion. The first cube is 80 by 100 by 3. The second 68 by 83 by 3, so that we have a lip so that the lid centers itself. Then we have a difference to take some holes out. These are tiny holes in the corners. If you did want to screw the lid down, those could be drilled out appropriately and mounting it firmly. A lot of times it snaps into place just fine. The last cylinder, if we take that out and re-render, you'll see that that's the center hole where the LED disc can clip into place. Finally, we have the Nano case. Again, it's set up as a difference and a union. The union really is just one piece, just the original block, of which the rest will be hollowed out. there's a main hole through the whole thing to allow the nano to show completely through. If we take that out, that fills that in. We put that back in, and then if we take out the next slot, that's where the nano actually slides in. You can see how that part operates. The final assembly goes together something like this. You can test the circuit, see things are working well. You have the 5-volt ground and data line wired up and soldered in place. The nano should slide into the insert. And the insert should set into the bottom of the base. The LED disc snaps into place in the hole in the lid. And then the lid snaps down. And with power, it's ready to go. Another interesting use of this device is illuminating solutions that have suspended particles. A true solution transmits the light, but suspended particles scatter the light, making the beams of light visible like headlights on a foggy morning. The Tyndall effect is the name given to this scattering. The sample shown is water with a little Nestle's Quick mixed in. It demonstrates the Tyndall effect for a surprising length of time. I thought it would soon settle out, but it worked well for over 3 hours, as seen in the time lapse.